Hi everyone, and welcome to another particular live webinar. I'm Mauro Servienti, and today I'm joined by my colleague Sean Farmer, and of course our guest Elton Stoneman. Elton is an independent consultant, Microsoft MVP for systems integration, and have been delivering successful solutions for more than 12 years. Today, he will show how to use messaging to power front-end applications. Elton, welcome.
Thank you very much, Mauro. Thank you everybody for joining. If you've seen the others of these, this is the third that I've been doing with the particular guys. Hopefully you found them useful, and this is one that it's different from the original plan. It was originally going to be about transactions and boundaries and bounded context, but from the previous two webinars, we had a lot of feedback saying how do you use messaging and still communicate back to your user? How do you power a front end with messaging behind it? So that's what we're talking about today. So here's what we're going to go through. We're going to build. I'm going to walk you through a little solution that I've built, which will be on GitHub later on in the week, which you can play with yourself. So it's all about using. It's a very simple Twitter clone. So I've got a basic website where I can go and send a message, and it gets broadcast to everybody else who's connected. So it's pretty straightforward stuff. We're going to walk through the key features of that solution and how it's relevant to what you might be doing yourself, and some of the pitfalls in how you design that sort of stuff. So we'll talk about that channel between your back-end process and the end user. We'll talk about broadcasting to multiple listeners at the same time. We'll talk about targeting a single response to a single client, so the person who initiated the original workflow, the person who sends a message to be sent to everyone. We're going to reply to them and say, yep, everything was fine. So we're going to target a particular user. And then we'll wrap up by looking at what we get from having that messaging back end behind our website. So the fault tolerance we get, the ability to replay messages, and how we can scale, how we can deal with throwing more web servers in and making sure we stay connected with our clients and can give them the same experience. So that's what we're going to cover today. So the first issue you've got when you've got messaging in the back end and you want to communicate to your user is you need a channel. You need something that exists between your processing system and the end user, something that lets you do messaging type patterns, but from the back all the way up to your client. So broadcast, where you can say to all the clients who are connected, here's something for you. Publish subscribe style, so taking a messaging pattern but expanding it out to the end user. And also the targeted response, so saying here's a single client in the request response style, maybe you've asked me to do something and I'm going to get back to you now and tell you how it went. So the idea of the channel is that behind the core system, there could be anything. So behind your web server, if you're using a web server, you could be using messaging, you could be doing processing within the web server itself. It doesn't really matter. That's not important to the channel. The channel is your callback mechanism to get information out to the client, to push out to the client. And what you're going to use for that channel, excuse me, it depends on what it is you're building. So if it's a mobile app, well, most of the cloud providers, Azure and AWS, have a mobile push solution. So you can send push notifications out, again, broadcast or targeted. If you're building a web solution, which is what we're going to look at today, then we've got WebSockets, which are a core part of most web servers and most modern browsers, modern going back a couple of years. So if you're using WebSockets, you can be pretty sure that most of your clients will have the ability to join in. And the last resort, if you haven't got those sort of things that allow a two-way communication, is polling. So if your front end, if you have to support an ancient browser, you don't have WebSockets, you can't have a two-way connection with the server, you will have to poll it periodically. There are definite downsides with that, so it's to be avoided if you can avoid it, but sometimes you can't. But today we're going to look at WebSockets, and specifically SignalR. So SignalR is a component of ASP.NET, which you can get from NuGet, and it adds that WebSocket two-way communication from your web service, from your website to your end users. It's a wrapper for the WebSockets API, which is a core part of the HTTP spec. And it lets you have a persistent connection from a server to a set of clients. provided they don't navigate away. So if you're building like a single page app, which is what we've got today, then when your client connects, you've got a persistent two-way connection between your server and your client, and you can do things like in your .NET code, in your .NET server, you can make a call which happens client-side. So the server can say, for all clients, now do this, and invoke some JavaScript code that runs on the client, so inside the browser. So you're pushing out code to execute from the server. And conversely, you can, on the client side, you have JavaScript code that connects to your hub, your .NET hub, and your clients can invoke server calls, so they can make effectively .NET calls across that web layer using the persistent connection that you get with SignalR. Okay, so let's have a look at what we've got so far. So we've got a really simple web app. It's using ASP.NET SignalR as the channel to communicate between the web server and the end users, but the back end is all powered with RabbitMQ. So as we've done in the rest of this series, I'm using a different transport each time, partly so that if you're following along with the demos, you get to use different messaging technologies, so you get to experience how they work and what's different about them. And Rabbit is particularly good for this particular problem. It has some functionality which isn't core functionality for all the message queues, which enables some of the patterns that we're going to see now. Okay, so let's switch to my virtual machine, and I'll fire up a whole bunch of browsers, and we'll see my little chat application. So I've got Chrome, I've got Edge, and I've got Firefox here, and each of these browsers I'm logged in as a different user. So with the presenters here, we've got Mauro, we've got Sean, and we've got me. It's pretty straightforward stuff, so all I do when I've logged in is send my message. So I say hi, and then you see it appears in the other screens, and I get a little notification telling me that something's happened. So at the same time, it appeared on all those client screens. So Sean replies and says, hello. And we see that on the other screens, and Mara replies and says, hey. And we instantly get notifications. This is our broadcast to all clients. So when you click send, what's happening is SignalR is pushing that message out to all the clients that it knows about. In this instance, I've just got a single web server. So my web server has got a persistent connection to these 3 clients on the different browsers. And when we get a broadcast notification, we push out the same message to all of them. So let's see what the code is doing for that. So we'll start backwards, and this is the SignalR component. So we're going to get to the messaging in just a second. The SignalR stuff is listening to a queue. So this is my RabbitMQ queue, and it's listening for a specifically named queue, which is the broadcast messages from my notice board. So we'll see how messages get in there in just a second. This is when the web server has received a message, so someone has sent a new post to go up on the notice board, and it reacts to that in this new mail method. And what it does is it takes the send mail request, which is the actual message that's got broadcast by it's got sent by RabbitMQ, and it's a pretty straightforward class that just wraps up what I need to have in my message, which is the sender, the content, and the date that it was sent. Builds that into a model, and then it calls clients.all.newMail. Excuse me. So that's saying this is the broadcast part. So this is saying all the clients that this server knows about, invoke the new mail method on them locally, and that new mail method is going to invoke some JavaScript. So in my scripts for the application, I've got a client method called new mail, which gets an object. So we use JSON in between. So when the server sends that mail model object, and I've realized I called it mail model, which is something slightly different than what I'm trying to get across. Class name's very important. It gets serialized as JSON, and then the JavaScript picks it up and it can access the properties. So I've got a common method here for formatting the message to build up my panel. So just to build that panel up, put the content in, and it gets shown. It gets added to the screen. So this new mail method is what gets called by the server on all the clients that are connected, and that's what pushes that new message out. So how does the send mail message get sent? Well, when you click send, then on the hub, this is the send method here. So when you click send, it invokes a piece of JavaScript running locally on the client in my Edge browser, and that talks to the server and calls a send method. So this is calling C# code, sending it two strings, which is the name of the sender and the content for the message. That code lives in my SignalR hub. And the send method just calls onto a queue and calls publish send mail request. So we build this send mail request object, which is the message that's going to get sent on RabbitMQ, and I call publish, and we send it with the properties that we're interested in. So there's a central queue that I use here inside my web server where all the messages get published. So whoever's connected, we send the message on the same queue, which is actually going to be broadcast to anyone who's listening on the RabbitMQ topic. So we'll quickly just have a look at this queue class, which wraps up our queue access. So this is taking care of a whole bunch of stuff which is to do with MQ. So as I've done previously, you kind of want to abstract the queue as much as you can. So in an ideal solution, you'd be able to swap in different transports. You'd have an IQ interface, and you'd have dependency injection, and you'd be putting in whichever transport you wanted to use for the environment that you were running in. For a simple demonstration, this is specific to RabbitMQ. So I pull out from configuration where my RabbitMQ host lives, because with Rabbit you have a separate broker, so I have to send it to a separate machine, and then I create all the things that I'm interested in, the messaging components. So this is a publish subscribe model. So when I get my send mail request, I'm going to publish it on a topic, but in RabbitMQ terms, that's called an exchange. So topics with queues in other transports are called exchanges and queues in RabbitMQ. So I've got my notice board exchange, and then I create all my queues that I know that I'm going to be using in my solution. So in the queue class, it's just a bit of setup work. If these already exist, then nothing happens. It's fine. RabbitMQ can cope with that. And I also create a reply queue, which we'll come to a bit later on. So when we call publish, and we take my message, which is a team message. In this case, it's the send mail request message, and then I create some properties, and I pass in alongside the message. So this is part of the functionality we get from RabbitMQ, which you don't necessarily get with all the transports, is that alongside the message body, I can send some properties. I can send some metadata that flows with the message. So in this case, I'm including type of message so that when the handler picks it up, it knows what it's got to deal with. And I'm also optionally including a reply to address. So if the handler needs to send a response message, then it knows where to send it to. With RabbitMQ, it's pretty low level, so it just expects me to send some bytes. My message body is going to be a byte array, so I do my own serialization into JSON, I do my own encoding into a byte array, and then I call publish, giving it the exchange name and a queue name optionally, and then the metadata and the message body. So that message drops into the RabbitMQ exchange, and then that gets pushed out to all the queues. Okay, so let's have a look at how that actually looks, taking a step back. So when the user clicks on the send button, as we've seen, that invokes some JavaScript on their browser, which ultimately calls into some .NET code on the server. And that .NET code drops a message onto the exchange. So we're making use of our channel, which is a two-way channel with SignalR that lets the client send into the web server, and then the web server drops that message on the RabbitMQ exchange. There are queues connected to the exchange, bound to the exchange, which means they will get a copy of the message that gets dropped on. So each of those queues will get a copy of the send request message. And then if there are handlers listening on those queues, they'll get a copy of the message and they'll be able to react to them. In this case, the web server itself is listening on that queue. So it's dropped the message on the exchange, but it's also listening on its own queue, so it will receive a copy of that message. And when it gets that message, that's when we do our broadcast to all our connected clients. So we receive the send mail request message, we build it up into a model, and we push it out to the clients. The clients get that in the form of a JavaScript invocation with the mail message properties, and then they render it for the screen. And one of the advantages very early on with having our queue there and our topic or our exchange is that it's pretty easy to scale up. If we've got multiple web servers connecting to multiple clients, then all we need to do is make sure they subscribe to their own queue, they'll get their own copy of all the messages, and then they push out to all the clients that they talk to. It's a message amplification. So this model, as you see, it's a funnel. So the message comes into the exchange, it gets amplified out to all the queues that are connected to the exchange. Each of those queues has a listener, it happens to be a web server in this case, and they amplify out the message to all their connected clients. So if we need to add more servers, we just add more servers and we configure additional queues, or we can have that additional queue automated, the creation automated as part of our setup. So in order to scale, we just throw more servers at it. It's pretty straightforward stuff. And we're taking the messaging paradigm, the publish-subscribe that we're doing at the RabbitMQ level, and we're taking that whole paradigm and pushing it through for the rest of the workflow. So effectively, you could take a slice of this diagram and say we've got publish-subscribe happening at all the different levels. So we're using one simple pattern and just amplifying it through the whole stack. Okay, so the broadcast notification stuff is actually fairly straightforward. We get a lot of the functionality from the channel, which knows about the clients that are connected, and all we've got to do is push that message out to all the connected clients, and then they'll react to it as they're told to react. The second part of this, which in some ways is more complex, is a targeted response message. So we saw, although I didn't dwell on it, we saw a couple of toasts popping up when you send a message. One says that it's been saved, and the other one says that it's been broadcast. So there are different colors to make sure you can see the difference easily. So there are different handlers there that are doing different things when they receive a copy of that message, which is easy to do because we've got an exchange with several queues listening, so I can have several handlers getting a copy of the same message, doing their own work, and then sending a response back. So let's have a look at how that response stuff works, because that's the core to this. And the second part of having that channel open to the client is being able to give one particular client a specific message. So if I switch back to my desktop, and we'll just send another message so we can't miss it. And I've got those two posts. So, I've got timestamps in here so that we can see that my mail got saved. And when you pick up the demo code, you see there is a real database here that it gets saved to. And the timestamp tells me the difference it took between the handler receiving that message and persisting it to the database and sending a reply. And the other toast, it's telling me that it got broadcast. So that's the web server itself saying, hey, I've got this message, I've sent it on to all my clients. So we're using obviously the same channel. So we're using SignalR to do the broadcast. And SignalR has a notion of connection IDs, so you can uniquely identify one particular client, and then it's up to you to tie that in some way to your user ID. So let's see how that looks. What we've got here in the code is I've got a reply handler which lives inside the web server. So just as with the persistence part of this that we'll see soon is listening for a send request mail message object, we've got the web server itself is listening for events that have been sent on the reply queue. So I'm listening for two different types of message, either a mail broadcast event, which is what shows my green toast to say that the mail's been shown to all the connected clients, or I'm listening to my mail saved event, which says it's been persisted and we can let the user know that their message has been safely saved. So the same queue, and I listen on for two different types of messages, and the queue I'm listening on is my reply queue name. So this web server has its own dedicated reply queue for messages that it's sent out. So when clients send a new notification from their browser, the web server here will add its own reply queue name to the message. And when it gets processed, the handler has got an address it can send a response to. And now this is what the web server is doing in this handler, is waiting for any responses that have come back to that send mail request message, which it broadcast on the topic. So when we receive one of these events, we do the same sort of thing. We just make a model, a response model, to send out to the client. and then we call send. So we've got this, it's a dictionary that is our link between the user ID, which means something to us but not to SignalR, and the connection ID, which is what means something to SignalR. So when we get our response model, we've got the sender, which is the name of the person who sent the message, and in our dictionary, if they're connected to this web server, we'll have a lookup that says this user ID is actually this connection ID. So in the send method, we've got a model to send out to them, a response model. We check to see if they're connected to this instance. If they're not, forget about it. There's nothing much we're going to do. If they are connected, then we call, again, this client's connection is part of the SignalR framework. I can call one specific client with the connection ID and then call show response. So that's different from the previous handler where I have my request message where I was calling all clients and I was calling send you a new mail. In this case, I'm calling one specific client and I'm asking them to call the show response method. And again, that's a method that lives in our JavaScript. So in my notice board, I've got a client method called show response. And what that does is it uses Toaster, which is on the NuGet package, to show those attractive little toasts which disappear after a few seconds. So the show response is fairly generic. It will show, it gets called whether it's a saved event or a broadcast event, and it just shows slightly different UI depending on what it's got. So so that's how we do that's how we exercise both sides of the channel. So our client's connection on the server is our list of persistent connections. We can either specify one of them and send it a message, or we can broadcast to all of them and give them a message. And the way we build our user connection lookup is, again, with using exactly the same channel. So when the user first connects on the page, in our initialization method, we make a server call and we call register user, and we pass them our user ID. And that register user call, which again lives in the hub because that's our connection from the server to the client, is this register user method, which just adds that username, user ID, and the connection ID from SignalR to our concurrent dictionary. So that's our lookup that says this user ID is connected to this server, and here's the connection ID if you want a direct channel to them. And if you don't want a direct channel to them, that's fine because we've got an all clients collection, and we can broadcast everything to all clients. Okay, so that's how the web server is pushing out those toasts. But where do the events come from that it's listening to? So it's listening for a mail broadcast event and a mail saved event. So those are the handlers that are picking up the original send mail request, and they're going to do their own work and then send some sort of response event. So one of those is a console app here. And this is the persistence part of it. So I've just got a right line here so we can see what's actually happening. Inside the console app, I'm using the same queue class. So that's a core class that's been part of a library which I can use around the solution. So everything's using the same queue abstraction. And I'm listening for send mail request messages. So I'm listening on my queue, which is for the persistence message handler, which is attached to that exchange. So this is part of the topic broadcast mechanism. So I will get a copy of the send mail request message, and when I do, I'm going to call this save mail method. So that does my write line, so that I can see that something's happening. I put the details of the mail into my database, and I'm using HBase here just to keep the technology stack interesting. And then I do queue.reply, so passing a mail saved event. So I tell it that, yes, I've got your message, it was all fine, this was the sender, this was the time they sent in, this is the time I saved it. And that's what powers that toast that tells us the difference in time between sending the message and it being saved. And I've got a catch block here too, which lets me send a different type of event, a failed event saying that something went wrong, and we could show that in a different toast. So there's an opportunity with our persistent channel from the user and our abstraction of the processing layer from the messaging layer at the back, we can send a different type of message that says, yes, everything was fine, the request you made has been processed, or we can say something went wrong and we need to do something about that. The reply is just a wrapper that does the same sort of thing with the publish, but it extracts the message queue, the reply queue name that we got from the last message. So that metadata that flows along with the message that says here's the reply to address is wrapped up in the queue class. So when I receive a message from my listen method, I pull out the reply to address. I keep a local copy of that, so I always know the reply to address that the last message had. And then if the consumer calls reply, I will send the message back to that queue. So it's just a little bit of sugar to make it easier in the consumer code to know whether you're sending your own message or replying to one that you've just received. Okay. And the second event that we listen to in our reply handler, so that's our mail saved event. We've also got the mail broadcast event, and that's coming from the web server. So the web server itself is listening for those send mail request messages, and when it gets them, it does the client all and broadcasts out the new message to all the connected clients. But it also does a reply. So when it's done the client all, new mail, it does the queue reply and it sends a mail broadcast event, and that's how the front end that's listening for that same message can differentiate between the events that have happened by the message type. It tells it when we were broadcast, which again, I show up in the toast so I can see the amount of time taken between the original send and the processing that's happened. And again, there's a catch in there, so if needs be, I can say something went wrong, the broadcast failed. I can show that to the user, so I've got that channel to tell them something went wrong as well as being able to tell them that everything went right. Okay, so that's how we target responses. Again, the core part of this is having that communication between our server and our end users that we can use in different ways, and we can use it for targeted responses with SignalR just by picking out a particular client connection, which we do we have to do our own work to connect that to the message that's going through RabbitMQ. We pull out the sender and we have to look up what their active connection is. So with our targeted response, we've got our exchange on the left, which is where the send mail request message goes in. That gets amplified out to all the queues, and then the listeners on the queue get a copy of that message. So the web server gets a copy of that message, and the handler, which is our console app, gets a copy of the same message. When the web server sends that message, it adds a reply to address. So it's got its own dedicated reply queue where it will listen for responses to messages that it's sent out. So remember, a web server might have dozens of clients connected, and it will be sending messages on behalf of all of those clients, but all the responses will go to a single queue for this web server. So when it gets a response message, it will be related to a client that it's connected to, and it can do the targeted response or the broadcast. So when it publishes that message onto the exchange, the web server includes a reply to address, which is its own address. So everything is wrapped up in that message. With RabbitMQ, because we've got the separation of the message body and the metadata, we can do that very cleanly. So our message body contains the stuff that we're actually transactionally interested in, the name of the person who sent the mail and the content of the mail. The reply to address flows along with it. We don't have to pollute our own domain objects with stuff like the reply to address. With different transports, you don't necessarily get all that functionality. So if you want to be able to use different transports, or if you want to completely abstract the transport, you need to take care of this stuff yourself. So in that case, you'll be sending an envelope, a message envelope, and you'll have your own body and your own metadata. So your body class is still your transactional class that says, here's a mail that I want sent, here's the person who sent it, here's the content, and your envelope will have additional stuff like the reply to address. With Rabbit, we get that stuff for us as part of the framework. And then the web server listens on that queue. So when the processing has happened for the send mail request, any responses come back in that queue, and the web server will pull them out from its own dedicated queue. So what's happening with the handlers? So we've got two handlers. The first one is the database handler. So it gets the send mail request, saves what it's interested in to the database, and then it sends a mail saved event to the queue. And that's what the web server will pick up and act on and send the toast to the relevant user. But it's also got the opportunity to send the handler failed event so that we can show a different message to the user. And with the web server, it's exactly the same principle. So the web server listens for that send mail request, it broadcasts the mail data to all the clients who are listening, and then it sends a mail broadcast event to the reply queue, which could be, in this case, it's its own queue. It's a queue that it's listening to and nobody else is listening to. But if we had a more distributed system, then it would go to the relevant queue for the server who has the client connected. And again, we've got the option of sending a more generic failure event if something's gone wrong with our processing. And when the web server picks up those response events, then we've got the option to look through our list of connected clients. If the client this message relates to is connected, then we send them the update and they get those toasts. The other clients are still connected. There's still a persistent connection between Mauro's browser and Sean's browser, but they didn't initiate this workflow, so I'm not going to give them the update notification. Only the originator gets those response messages. But, so in the solution we've got so far, we've got SignalR as the channel between the server and the clients, and the back end is powered by RabbitMQ. But you can do most of this just with the channel. The channel is powerful enough. It has the mechanisms to broadcast to clients. It has the mechanisms to send a message to a particular client. So what do we actually get by putting messaging in the back end of this? So with SignalR, I could just have all the processing contained within my web server. So client sends a message, web server gets the request in the SignalR hub, and it broadcasts out to all its clients, and then it saves the database, and then it sends a specific response to the client who initiated the message. The whole workflow can be encapsulated in process on the server without having to introduce another component, which is the message queue broker, without having to introduce other handlers. So what do we get if we do take on the extra workload and the extra components and the extra moving parts? So this ties us into the previous two demos. There's a couple of things we get, and the first is fault tolerance. So if there's a problem with one of our handlers, then our workflow can continue without breaking. If we had the whole of the workflow being processed inside the web server, if it couldn't connect to the database, then we need to make a decision when we write the database connection code to say, what do we do next? How long do we wait when we've got a user sat on the end waiting for a response? How long do we wait before we give up and don't do the save? And then what happens to that message? Does it never get persisted? But by having our message queue in between, we can take care of a lot of that stuff. So let's have a look at what happens if our handler is offline. So let's just double check. This is my console app, which saves the data to HBase. These are my connected clients. So at the moment, if I do message 333, I get my two toasts about it being saved and about it being broadcast, and all the clients can see the 333 message. If I kill my console app, now there's no handler listening for the send request message that's going to do any saving. There's still a handler listening, which is the web server, which will do the broadcast, so I can do my message 444. And it still gets broadcast, and I'll still get the toast saying that it's been successfully sent. So half of the workflow has worked, and the kind of the core functionality as far as the user is concerned is there. They might notice that they don't get the blue message, but they might not. And similarly, I keep sending messages, and they keep being broadcast. I keep seeing my toast to say that the broadcast worked, the message has been seen by connected clients, but it hasn't been saved. So what happens if I then start the handler later? So then I see my toasts. So the handler picks up those messages which were in the queue, and it does the processing that it needs to do. It makes the save. It sends the mail saved event. And because the web server is still listening to its private queue, it gets those event messages, and because the client's still connected, it sees the toast to say that the messages you sent a little while ago have just been saved. So we've interrupted the workflow because part of our solution wasn't functioning. But when it came back online again, the workflow all got completed. The user saw the end notification that everything worked as expected. And if we move on to, I won't do 666, then I get my two notifications at the same time. So when we're back online, everything works as expected. If part of our solution is down, then the workflow as a whole can continue to work. And that's because of the message queue in between. So it would be very difficult to do that if you were doing in-process processing. So if everything happened inside the web server, you wouldn't be able to replay the message that said, you need to save this. if you couldn't contact the database, you'd have to take exception handling to deal with the fact that I've got a message here that hasn't been saved. What do I do about it? But with the message queue in between, those messages that say I've got a whole bunch of send mail requests here, they live in the queue, which is durable, so it will stay there. And when the handler comes back online, it picks up all the messages in the order that they were sent, it does its processing, and because the whole rest of the stack is still there, it just slots back in. It sends its reply messages, which go to the queue, which is the dedicated queue for the web server. The web server picks them up, and because the client's still connected, it can send the notifications to say, hey, it was a bit late, but we've saved your stuff. And the second part of the benefit you get from having messaging at the back of this kind of solution, firstly, yes, you can do that fault tolerance. Secondly, when it comes to scaling, part of it is easy. So even if you only had SignalR, the broadcast notification is fairly easy. The more clients you've got, then you can push the message out to as many as you've got servers. And even with our messaging component, we get the added benefit of having our publish subscribe. So you send to one central location, and the message gets amplified. But even with the messaging, the targeted response gets a bit harder when you are scaling this stuff out. So let's think about that. So if I've got two web servers hosting the same solution, I've got them load balanced, and I've got clients connected to different servers, then SignalR has got some fault tolerance built in, so it will try and keep connections going if something happens to them. So in this case, I've got on my server on the left, I've got myself and Mauro connected. I've just sent a message, and then I lose my connection. So that could be because I'm on a train, or I've had an outage. Nothing to do with the solution that we've built. So one of my clients has lost a connection. It's not a fault with any of our kit or any of our design. It's something that's happened with the client. They're no longer connected. Now that's fine, because SignalR sends heartbeats to the server, and if the connection goes down, the next time it sends a heartbeat, it will re-establish the connection. But because we're load balancing, it might go to a completely different server. So the situation now is I sent a message to the server on the left, it did all the processing. When it comes to reply to me to say, yeah, everything went fine, I'm no longer listening to it. I'm listening to a completely different server who has got no notion of the fact that it was me that sent the message. So if everything's done inside the server, then there's no real opportunity for dealing with the fact that clients are going to move between servers, which they will as this gets bigger and bigger. It won't just be a couple of web servers, it'll be dozens. And you would have to have some sort of custom mechanism to communicate between those servers if you wanted to deal with the fact that a client has moved on, but I've got a notification to send them. And actually, even with the solution that we've built at the moment, it doesn't handle this scenario. So same scenario, I've sent my message to server 1, it did its processing, and then I've moved on to server 2. Well, when the database sends its mail saved event, and when the server sends the mail broadcast event, it'll go to the reply queue for the original server, which is the wrong queue. It's not really the wrong queue because that's the address that it was told to send to, but it's wrong now because I've moved on and I'm listening to a different server. So even with our current implementation, we can't fix this problem of clients moving between servers because the channel has been broken and it's been re-established somewhere else. But with messaging, with a slight change to our design, we can accommodate this, and we can allow it to scale, in theory, indefinitely. So instead of having a single reply queue that each server has, we flip that on its head, and we make the responses publish subscribe as well. So the database handler and the web server would instead of sending their mail saved events to the queue of the web server that initiated the workflow, they publish an event to a topic, a different topic, saying something's happened. And all the web servers would listen to would have their own queues listening to that exchange, so they would all get a copy of that. So when the server on the original server gets a copy of my mail saved event, it knows that there's no longer a connection from that user. So it still gets the message from RabbitMQ, but it doesn't go on to try and push it out to a client that it knows isn't connected anymore. the new server, which didn't originate the workflow, also gets a copy of the same mail saved event, and now it's got a connection to the client that initiated the workflow, so it can do that push out to notify the client that what they requested has been completed. So with messaging at the back end, because we can mix and match our patterns, we can deal with these scenarios of and accommodate the fact that the channel got broken and re-established. So SignalR doesn't do that for us, but we can do it ourselves just by changing the way that we broadcast our completion events. Instead of using a specific reply to a specific queue, we can broadcast to say, this thing has happened, and any consumer that's interested can act on that. So a lot of the time servers will get event messages that are for clients that aren't connected, and they won't do anything with them. But when they are connected, then they'll get the notification, and it doesn't matter if the client has moved between servers since starting the workflow. Okay, so we've got a bunch of time for questions.
Yeah, I just wanted to chime in there and ask you a question about your solution. How could you explain the difference between what the architecture that you're showing up here, which is a broker style architecture, to something that would be, as opposed to kind of a distributed architecture where, you know, if you're using MSMQ or any kind of single queue per node style architecture? Can you...
Yeah, absolutely. So yes, that's a good point. So as I said, there are certain aspects of RabbitMQ that we're taking advantage of in this solution, which mean it might be difficult to replicate in using a transport that doesn't provide them. So RabbitMQ is a centralized broker. So no matter who you are sending messages to, your endpoint ultimately is the RabbitMQ server. So in my case, if I flip to it, you'll see that what I've got running is I've got a VM here which is running Docker, and I've got a Docker container which is my RabbitMQ server. So when my client wants to connect to RabbitMQ, it needs to make a connection to a configured address, which is, in my case, where are we? That's the address of my virtual machine that's running that Docker container. So it's not like something like MSMQ where you might have several queues all living on different machines, and you would need to know where to send your message to. With RabbitMQ as a centralized broker, all messages go there, and it decides what to do with them. It's got a lot of capabilities for fine-grained routing of messages, so you can route messages to individual handlers without knowing about those handlers by saying this is a message that is relating to the user Elton, and only handlers would connect to a queue, but they would filter incoming messages to say I'm only interested in messages with perhaps this message type that have this username somewhere in the routing key. So that's one of the things you get from Rabbit of having a centralized broker, is that it can add a lot of extra value at the cost of having a centralized component that you then need to make resilient. So in my case, for a demo, it's fine, I can spin up my Docker container, but in reality you need multiple servers hosting that broker so that you got the resilience, and it's another moving part. So you kind of need to get a balance between I don't care which transport I use, I'm going to make my solution transport agnostic, with having to compromise what you want to achieve, because some of this stuff is very easy in Rabbit. If you had to write a custom solution using any transport, it would get significantly harder. So sorry, that was that was Sean's question.
Yeah, that's.
Okay, cool. So yeah, I know the guys have been collecting questions as they've been running in. So very briefly summarize, the key thing here when we're talking about messaging powering a front-end app is that the messaging itself can't do it alone. There needs to be a channel somewhere that the client that knows about clients and can push out to clients. So we've used SignalR in this case. You can use a notification hubs if you're dealing with mobile apps. And the advantage of having that channel is that it allows you to follow through with your messaging pattern. So if you're using publish subscribe, you can publish your message to a topic, to an exchange in RabbitMQ. It gets amplified out to all the queues who are listening with any listeners, and all those listeners publish them out to all their clients. So you can take that whole messaging paradigm and run it through the whole slice of your stack. And the same with request response. You can echo the fact that I've got a request for a specific queue and take that in SignalR and make it a message that gets sent to a specific user. So if that channel can do the same thing conceptually as your message queues, then you're dealing with a very neat way of implementing your solution. So you can do it just with the channel, but you lose a lot of the higher level stuff. You lose the ability to cope with faults, to cope with temporary failures by having that durable queue that lets you pick up messages later and act on them. And you have to deal with the fact that any kind of solution that needs to either be resilient or needs to be able to deal with lots of load has to be able to scale. And if you're just using individual nodes that do all their own processing and know all about their own clients, it's very difficult to cope with that situation of a client moving between nodes. You need something centralized that can coordinate between them. And if you're going to have that centralized component, then a message queue gives you a whole bunch of extra benefits. So yeah, so that's our summary. All this stuff will be going up on GitHub during the week, and I'll be blogging about how you can get set up and run it locally and all that sort of stuff. So hopefully this is something you can pick up and play along with.
So thank you very much, Elton. We have a couple of questions. I'll start with the first one from Morten. And as expected, the first question is about the same thing done with the service bus. And well, let me first start saying that Sean and I are going to handle this in the next webinar that will be in a couple of weeks. And we are basically going to implement the same thing that Elton has showed us today using a service bus. I'll read the question so anyone is aware of it. The scaling here looks very simple, having each server instance listening to their own queue. Is it possible to do the same with an service bus? For example, if I host my endpoint in Azure and scale it out to 3 instances, can these 3 instances listen to their own queues so that all 3 get a published message? Out of the box, the answer is basically no. So there's a couple of options to do the same thing with a service bus. One is to use callbacks, and I can anticipate that callbacks will be revamped with the next release of a service bus. So there will be much more options on the table. And as Elton mentioned at a certain point during his presentation, the replying back to a specific node is not necessarily the best way to go. I mean, Elton showed a case where is the client disconnecting and reconnecting back to a different server, but what may happen is that one of the instances of the web servers that is serving clients dies while waiting for a reply. So all the clients are forcibly disconnected and will reconnect back to different web server instances. But that means that in the Elton samples, the queues attached to the exchange of RabbitMQ will be deleted and messages will be missed. So correct me if I'm wrong, Elton. And the solution to the problem is basically to introduce a backplane. What a backplane is basically a set of queues or a storage that will be shared by all the running instances, so all these scaled out instances that allow these instances to talk to each other, saying, we are living in a competing consumer scenario, so I received an event saying that something has happened, but I do not know what to do with this event. Do some of you guys have an interest in this event? So if yes, do whatever you want. That's the basic idea of using a backplane. And in the next webinar, we'll see how a backplane with an service bus and SignalR can solve the same scenario that Elton just showed us.
Absolutely, from just to chime in there with the question about scaling up, what you need to bear in mind is that although it's very easy, especially in a cloud scenario, to scale up and just add 10 more servers on, your server code needs to be able to bootstrap itself. So if my server only operates if it's got its own dedicated queue that's connected to a backplane, or it's got a queue that's connected to a topic, then it needs to be able to set that up when it starts. So you need to be able to leverage some sort of entry point that says, I'm a new node, I've just been commissioned to join the cluster. I know I need to do these steps to make myself ready to work. So there's a point there which would be in a web app, it would be in global ASAX or some sort of startup routine that said, I need my own queue that's connected to this topic that I know about, and it would create it if it wasn't there. So no matter how you actually implement the communication, there's quite possibly a requirement for every node to be able to set itself up when it comes online.
Yeah, very good point.
Yep, so we have another question from Chris. He's asking if Rabbit can handle thousands of topics if we're using a topic for user in a common reply queue. Elton?
Yes, so yes is the simple answer. Rabbit does scale up pretty significantly. It's an implementation of AMQP, which is the Advanced Message Queue Protocol, which Azure Service Bus also implements. And again, you can do the same thing with Azure. You can just effectively spin up as many queues as topics as you need. Because of the extra routing capabilities you've got in Rabbit, though, you might not need to do that. So you may just have let's say in our example, we've got our saved events and our broadcast events. Potentially, we'd have different topics for those, and as we publish each message to the topic, we would include like a routing key that said this is the user that this message relates to, and then your handlers would subscribe to one topic, but they would give it the key that they were interested in, or a set of keys. So it would say, I'm only interested in messages that come from this user being an example of something that we manually add into the routing key to give a hint to the handlers that they may or may not be interested in it. So quick answer, yes, it does scale. Obviously, with anything that you need to scale up hugely, there are considerations of making sure it's all resilient together. But with the routing key stuff, you might not need to go down that route with Rabbit. Again, if you're happy to land on a RabbitMQ based or an AMQP based solution and effectively shut off other transport options, then you can leverage some of that stuff.
Great. So there's another question that is, what happens when the client goes off on a reply and comes back later? Does SignalR queue it up, the response, and send it later?
No, not automatically. So when I said that SignalR is fault tolerant, there's kind of limited ability for it to do that. So so out of the box, you don't need to do anything. You don't need to set up SignalR as such. You can just start programming, but you can configure it and say this is the lifespan of a connection, and if I don't get a heartbeat from the client, then I'm going to assume they're disconnected. Then what will happen is if the user's browser is still there, if they've dropped their connection for whatever reason, the next time it tries a heartbeat, it may go back to the same server, or it may go back to a different server, but it'll be a new connection with a new connection ID. So SignalR isn't going to give you the failover capability that says I need to send this message to this client, they're not here, so I'm going to queue it up and wait till they come online again. You don't get that from SignalR. If you need that, you need to do it yourself, which is where the kind of messaging part comes in. So the fault tolerance you get from SignalR is just trying to make sure that the client stays connected, but it might be a new connection. So it's persistent as long as it lasts. If it fails, it'll be replaced with a new one.
Yeah, if I may add a couple of comments, the SignalR does not guarantee any delivery, so there is no guaranteed delivery, and there is no durable messaging. So if we want to compare SignalR to a messaging infrastructure, these are the two things that we're missing.
Yeah, definitely. That's why I've been kind of keen to define it with that. It's a channel to the client. You can't visualize it as a queue between the server and the client. It's not doing that. It's just a connection that will push out a message if it can. If it can't, nothing happens.
I have one more, which is what about a single point of failure in the broker, in this case Rabbit?
Yeah, absolutely. So that's the key concern. If you take any kind of broker into your architecture, is that it becomes a single point of failure, but it's only a logical single point of failure, which is an important distinction because Rabbit is a enterprise grade messaging system. It's built to be clustered and run on multiple machines to give you the physical fault tolerance. So although in your little diagram that you draw of your solution, there might be one box that says RabbitMQ, and someone can say, well, what happens if the lines to those boxes fail? Actually, in reality, you may have 3, 5, a dozen RabbitMQ servers which logically form that single broker. So there's a distinction that I think you need to make between a logical point of failure and a physical point of failure. If you've got a single RabbitMQ instance, then yes, it's a single point of failure. If that machine goes down, no messaging can happen. But in reality, in a production solution, you wouldn't have that. You would have multiple physical nodes enacting that logical point of failure. So in theory, if one or more of them went down, you still have the capacity to keep your solution up and running.
Would it be true to say that using SignalR combined with RabbitMQ, they both can be used to build web smart client applications?
Yeah. I think that's kind of where I'm going here. So the examples you see if you start playing with SignalR, they're all kind of like this one. They're chat type things. They're multiple broadcasts. They're sending stuff to clients all at once or occasional replies. Actually, once you've got that persistent connection to your client, that enables you to make a much richer web experience. So there's no polling back to the web server to check for updates. There's no querying off to a separate API to say has this piece of work been finished or what's the status of this. You can be doing that all with your persistent connection. So the toast paradigm of the little pop-up that shows you something that's happened can be sprinkled throughout all of your workflows. So it can be there to say your basket has been saved, or you've added this to your basket, or this thing that's in your basket has just gone out of stock. So it doesn't have to be a connection that you can only utilize for a specific workflow. You can use it for your whole stack. So if that's a particularly good example. So if a whole bunch of people have added the same ticket for a concert into their basket, then how do you tell them that it's just been sold out? That's a good way of doing that. You've got your persistent connection. You can use it however you like, and you can make it as smart as you like. It does power a whole range of much richer web apps.
Great. We have another one from
and to add a couple of comments. Yep.
There's one or two more questions, I think. One is, what about admin tools? So I presume that Rabbit has its own administration tools.
Yeah, absolutely. Let me show you. So even with the even with running it in a container, which I've got now, the container's got Rabbit has its own web interface, so you can do a whole bunch of stuff here. So I can see who's currently connected. I can see the exchanges that are set up, which are some out-of-the-box Rabbit ones, and my notice board, the type of topic it is, and I can publish messages directly from the web interface. I can see the queues that are there, which are my two that are connected to my exchange and my reply queue, and I've got a whole bunch of admin options here. So I haven't really gone into it. I've tried to make, especially if you're going to pull the code off GitHub and start playing with it yourself, I've tried to make it as easy as possible to get going with this. So I'm using the default guest account, but you can have service accounts set up, and you can limit which parts of Rabbit they can access, whether they can send to certain topics or receive from certain queues. So you've got a fairly rich admin interface here. And there's an API behind this too, so you can you don't have to just go in and look at the web UI. You can power it through scripts.
So just a small comment on the previous question, and then we can wrap up. That is, the SignalR is not double linked to a web client, so it's not meant to work only with JavaScript, because there's a follow-up comment on this in the question window. And you can use SignalR from the web server and consume it from any type of client you like. SignalR is the ASP.NET implementation of WebSockets. So on top of WebSockets, built on top of WebSockets, and using SignalR there are clients that can be used from C# or WPF or whatever type of application. So it's not limited to web and HTML and JavaScript clients. That's it.
Okay, so as Elton mentioned at the beginning of the hour, this is the final presentation in the messaging webinar series. So I hope you've enjoyed it. I know we certainly have. And Elton, thanks a million for sharing your experience with us today. And where can people find you?
Yeah, thank you very much. So the guys in particular, it's been really good to do this series. I hope everyone's found it useful. I know all the infrastructure the particular guys take care of. So setting up GoToWebinar, you'll be able to download the video of this session and the previous sessions in a day or so. So thank you for all that. It's been really good. What am I doing now? Currently, I'm working on my next Pluralsight course, which is about HD Insight. So I've been quite fortunate in my last couple of projects to be working on big data stuff. So event hubs as the massively high throughput messaging system in Azure, and how you kind of what you can build on top of that with big data stuff that's being made easier and easier for .NET people in Azure. So that's my current thing. By all means, follow me on Twitter or check out my blog. So there's a whole bunch of stuff going on there, mostly about HBase and Docker and HD Insight at the moment, but it does change as the projects develop.
So that's all we have time for today. On behalf of Sean Farmar and Elton Stoneman, this is Mauro Servienti saying goodbye for now, and see you on the next particular live webinar.